All right. So for this, I want to talk about a couple examples of linear transformations that are of the form transformation of some vector x is equal to a matrix A times x. And we talked about how all linear transformations actually have a special matrix that does this. And so I want to look at these couple examples and then actually prove why that statement is true. So for the first example, I want to consider the transformation where the matrix A looks like this, 0, 1, 0, 0, 0, 0. And so here, if t of x equals A times x, then t is a transformation from R3 to R3. So it takes a vector in 3 dimensions. Oh, sorry, R3. Yes, so R3 to R3. So it takes a vector in 3 dimensions to another vector in 3 dimensions, but this matrix is special because of this row of all zeros down here. And so I want to look at what happens when I actually do take this matrix and multiply it by a vector of 3 dimensions. So, for example, suppose that x is the following vector, so just 2, 3, 4. Then t of x is equal to this matrix A times x. And if I do that, 1, 0, 0, 0, 1, 0, 0, 0, 0 times 2, 3, 4. And remember, the way to do this is to take the first entry in this vector and multiply it by the first column. So I have 2 times the column 1, 0, 0, and then I add that to, wonder if I can switch this color. I actually don't know how to do that. Something to learn for another time. Oh wait, actually, here we go. Let's use blue. Okay, I take 3 and multiply it by this column. So second entry times the second column, 0, 1, 0. And then the third entry times the third column, which would be 4 times 0, 0, 0. And notice I end up getting 2, 3, 0. So my first and second entries stay the same, and my third entry disappears. And so this is a special type of transformations. And here we say that T is a projection of R3 onto R2. So because this third column is always zeros, this third entry right here will also always be 0. And so in fact, if I were to take any vector x in 3 dimensions, so let's say it's a vector x1, x2, x3, it's always just going to be equal to its first entry, its second entry, and then a 0. So really, it's from R3 to R3, But since this third entry is always 0, we can kind of think of this as mostly just being in R2, since this third one doesn't really matter. So of course we still say from R3 to R3, but we call it a projection because it does really only keep the first 2 entries. Okay, the second type of transformation is what's called a shear transformation. So example, shear transformation. And a shear transformation is a transformation that leaves an entry of x fixed, meaning it stays the same. So for example, if A equals this two-dimensional matrix, or sorry, 2 by 2 matrix, 1, 3, 0, 1, I am going to claim that it will leave the second entry fixed always. So here, let x equal, let's say 4, 5. Then t of x here, if t of x equals ax, of course, is equal to a times x, which is equal to, again, the first entry times the first column. So 4 times 1, 0, plus the second entry, second column, so 5 times 3, 1. And here that gives me 4, 0 plus 15, 5, which is 19, 5. And so we see that the second entries stay the same. And really, I'll say that the book has a nice picture of this. We're really kind of, if you, the example in the book is a two-dimensional picture, and it kind of fixes the base of a square and then stretches the rest. So if you would like to see a visualization of what's happening in this, you can look on page 66. Okay, but what I want to get to with the rest of this is this theorem that we talked about last class. But actually, let me pause here, and I will do that in a second video.